we're going to talk about exponential models with differential equations. So in many applications, the rate of change of the variable y is directly proportional with the value of y. So for a lot of these, y is going to be a function of time t, and that would mean that dy dt equals ky. Now I want you to notice that this differential equation is separable. So I'm going to separate the variables. We get 1 over y dy equals k dt. And then I can integrate both sides of the equation equals kt plus c. And keep in mind that k is just some constant, and now c is another constant. From here, to get rid of the natural log on the left, I'm going to exponentiate both sides. And then we could say e to the kt plus c is e to the kt times e to the c. Keep in mind, e raised to a constant is just another constant. So I'm going to rewrite this as the absolute value of y equals just some constant times e to the kt. And we're going to end up dropping the absolute value, and I want you to notice that we get this equation right here. So we have our exponential growth and decay theorem. It says if y is a differentiable function of t such that y is greater than 0 and dy dt equals ky for some constant k, then y equals c e to the kt. So for all these problems, we're going to be using this differential equation and then also this y equation. C is the initial value of y, and k is the constant of proportionality. And then we have exponential growth when our constant of proportionality is greater than 0, and it's decay when the constant is less than 0. So let's go through a few examples. Starting with this one, it says the rate of change of y is directly proportional to y. So let's say you have a homework assignment or a test. As soon as you see this sentence, that should trigger in your brain that dy dt equals ky. And once you're able to use this differential equation, you're also able to use y equals c e to the kt. Just that one sentence says you're allowed to use both of those two equations. Then it says when t equals 0, y equals 2. When t equals 2, y equals 4. What is the value of y when t equals 3? So we are going to be using this info to get our c and our k. Once we do that, we can answer the question that they're asking. So let's start by finding c. I'm going to plug in t equals 0 and y equals 2. Notice this is 2 equals c e to the 0, so c equals 2. So I can plug that in. Now we need k. I'm going to use the t equals 2 when y equals 4. Divide by 2 on both sides. I'm going to natural log both sides. Divide by 2 again, and k is the natural log of 2 over 2. So I'm going to rewrite our y equals c e to the kt. And let's go through a few steps to make this look a little bit simpler. I'm going to start by moving this 2 in the denominator under the t. So I'm going to have t over 2 times natural log of 2. And then I'm going to use log properties to move this t over 2 up to an exponent. And now notice when I have e to the natural log, this equals my 2 that was out front times 2 raised to the t over 2. Now that it looks a little nicer, notice now we can answer their question. They want to know what is the value of y when t equals 3. So my last step is I'm going to plug in 3. And let's simplify. This is going to be 2 times 2 cubed square rooted, which is 2 times the square root of 8 which is 4 rad 2. So there's one example. And this one didn't really have much context to it, so let's do a problem that has some context in it. So this one says the population of bacteria in a culture increased from 400 to 1600 in 3 hours. Assuming that the bacteria population P grows according to the rate equation dp/dt equals Kp, where T is the time in hours, and then they have a few questions. So first I want you to notice that they gave you this dp/dt equals Kp. This is the same thing as dy/dt equals Ky, but now they're using P's instead of Y's, which is totally okay. But once they tell you you can use this differential equation, we know that we can also use, and I'm going to put the P in there instead of the Y, but P equals Ce to the Kt. So letter A says to find the value of K. So they gave us a little bit of info. They said that the bacteria in a culture increased from 400 to 1600. So we can say that 400 is C, that initial amount, and it grew to population P, 1600, in 3 hours. 3 hours is our time, so I can say 3 is T. So I'm going to plug those in. And let's solve for K. So I'm going to divide by 400 on both sides. I get 4. Natural log both sides. And we get that K equals natural log of 4 over 3. And that was part A. Part B, how fast is the population of bacteria increasing when the population is 3,000? So I want you to notice they're talking about a rate of change right here. So they're asking for the value of dp/dt. So we know that dp/dt equals K times P, and we figured out what K equals. K equals the natural log of 4 over 3, and so I have that times P. And they're asking for the rate of change, how fast is the population of bacteria increasing, when P equals 3,000. So I'm going to plug in 3,000. And we can simplify. We get 1,000 divide each of those by 3. And we get 1,000 times the natural log of 4. And if we want to do units, we're going to say bacteria per hour. And that is our second example. We have a couple different types of problems. Number 3 says an amount A increases at a rate proportional to its current amount. So notice, and they're giving it to you also, dA/dt equals Ka, where T is measured in hours. If the amount triples every 11 hours, find the value of K. So we have that A equals, since they gave us this info right here, I can use that A equals Ce to the Kt. And the info they gave us is that the amount triples every 11 hours. So it doesn't matter what my starting amount is. I could even say the starting amount is 1, and then if it triples, A would be 3. And I know that happens in 11 hours. So I'm going to make T equal to 11. And from here, we can solve for K. So I get 3 equals e to the 11K. I'm going to natural log both sides. We get natural log of 3 equals 11K. Divide by 11 on both sides, and K is the natural log of 3 over 11. We have one more example. This one says radium-226 loses its mass at a rate that is directly proportional to its mass. so loses its mass at a rate that is directly proportional to its mass. So notice that that is that differential equation. dm dt equals km, if m is our mass. Then it says if the half-life is 1,590 years, and if we start with a sample of radium-226 with a mass of 100 milligrams, and then we have our question. So part A, find the formula for the mass m of t that remains after t years. Well, we know that we have this differential equation, so then we also know that m equals ce to the kt. So I need to figure out c and k, and that will be my m of t equation. So to start, let's plug in what we know. And they told us that the half-life is 1590 years, and we start with a mass of 100 grams. So if we start with a mass of 100 grams, that means that c equals 100. So we know that. And to solve for t, we're going to use that the half-life is 1590. So if I start with 100, that means my half-life, I'm going to be at 50 when t equals 1590. So I'm going to plug those values in for m and t, and we can solve for k. So divide by 100 on both sides, I get 1/2 equals e to the 1590k. Natural log both sides. We get natural log of 1/2 equals 1590k. Divide by 1590 on both sides, and k is the natural log of 1/2 over 1590. From there, I can write my m equation. M equals my c, 100, e to the natural log of 1/2 over 1590 times t. Similar to what we did on one of the previous examples, let's clean up this equation a little bit. So I'm going to say this is 100e to the natural log of 1/2, or let's put the t in front. We're going to say t over 1590 times the natural log of 1/2. Use the power rule for logarithms. I'm going to say this is 100e to the natural log of 1/2 raised to the t over 1590. Notice your e and your natural log undo each other. We get 100 times 1/2 raised to the t over 1590. And that is your m of t. That is part A. Part B, how many milligrams of the original sample remains after 100 years? So for that, we're going to plug in 100. So I want m of 100. That's going to be 100 times 1/2 raised to the 100 over 1590. And we would type this into a calculator, but we should get approximately 95.734 milligrams. Letter C, how many years will it take for the sample to have only 3 milligrams remaining? So 3 is going to be an m, and I'm going to solve for t. So we're going to say 3 equals 100 times 1/2 raised to the t over 1590, and solve for t. So I'm going to start by dividing by 100. I'm going to natural log both sides of the equation. We get the natural log of 3 over 100 equals, and I'm going to bring the t over 1590 out front. I'm going to divide by the natural log of 1/2 on both sides. I'm going to show my work up here. And then I'm going to multiply both sides of the equation by 1590, so I get t equals 1590 natural log of 3 over 100, over natural log of 1/2. And that is your t. Okay, so those are a few examples of exponential models with differential equations. Thank you for watching.